In this video, we're going to do a series of short practice problems involving stoichiometry, gas laws, and energy. To start off with, we have this reaction. Ammonia gas plus hydrogen chloride gas will react to make ammonium chloride solid. If you have two containers next to each other, they will just form a white cloud in the air halfway between the two containers, which will slowly settle to the surface as a salt. So these two chemicals are a little difficult to deal with, because you really do have to keep them contained where they'll react with each other in the air, and then you're likely to accidentally be breathing them. In our case, we collect that solid, and we find that there is 27 grams of ammonium chloride that is formed. What we want to know was what volume of each of those gases must have reacted. How much must we have used if the gases were at 23 degrees Celsius and 0.97 atmospheres? So this involves a balanced reaction, stoichiometry, molecular masses, and gas laws. Go ahead and pause, give this a try, and see if you can find the volumes of those two starting materials. All right, if you're back, well, to start, if I want to know something about the starting materials, I need information about them. I'm not given any masses, I'm not given any moles. In fact, the only compound on here I'm given amounts of is my product. I have 27 grams of ammonium chloride. Well, that means I know an amount of one of my chemicals. I can use the balanced reaction to go from an amount of one chemical to an amount of any other chemical in that balanced reaction. As a result, I have 27 grams. I can do this. I can jump from one chemical to another, but I can't do it in grams. I have to be in moles. If we look at our balanced reaction, 1 chlorine, 1 chlorine, 1 nitrogen, 1 nitrogen, 4 hydrogens, it is already balanced. It's 1 to 1 to 1. My molecular mass for ammonium chloride, if I add up the nitrogens, the hydrogens, and the chlorine, is 53.49 grams per mole. So I have 27.0 grams of my product, but I don't want to be in grams of my product. So I need it on bottom so that I can cancel it out when I divide them. And I need it in a ratio to the moles, because I need to be in moles of my chemical so that I can find moles of my other chemicals. So I need a ratio of grams to moles for ammonium chloride, which molecular mass. It is 53.49 grams in 1 mole. I have about half of that. We're going to end up with about half a mole. 27 divided by 53.49 will give us 0.5047 mole of NH4Cl. with 3 sig figs. I have the moles of ammonium chloride. Now that I have the moles of one of my product, I can use the balanced reaction. It is 1 to 1. In fact, it's 1 to 1 for both of them. Both of my gases are going to have exactly the same amount. If I wanted to show it, I could say, hey, it's 1 mole of my NH4Cl solid for every 1 mole of my HCl that reacted. So I would have 0.5047 mole of HCl. And it's going to be exactly the same for the ammonia. I would have had a balanced reaction that was 1 mole of NH4Cl to 1 mole of NH3, and it would have been 0.5047 mole of NH3. What we find is because it's a 1 to 1 to 1 reaction, it's the exact same number of moles. Well, this tells me the moles of my gases. Each of them. Well, one of the questions we're trying to solve is what is the volume of those gases? To solve a volume, well, the only real way we have to do it, if you're talking about a gas, is pressure volume equals nRT, the ideal gas law. Well, I just was given moles. We solved it from the balanced reaction. We're told temperature, so I have the temp, and I'm told pressure. We can solve the volume as long as we use the right R value. R is a constant. We're in atmospheres. Remember that your R value in atmospheres is 0.0821. Atmospheres, liters, mole, and Kelvin. So I can solve the volume for both of these gases. So PV equals nRT. We want volume on its own, so I need to divide that pressure over to get volume on its own. My moles, 0.5047 mole. R of 0.0821. Atmospheres, liters, mole, Kelvin. My temperature, well, 23 Celsius, well, we have to be in Kelvin. So 23 degrees Celsius plus 273 for 296. We are 296 Kelvin. And our pressure, 0.97 atmospheres. What we'll find is that our volume is equal to 12.64 liters, and we had really just 2 sig figs. There was 3 from our moles earlier, there was 2 from our pressure, so it's going around to about 13 liters. And that's true for both gases. They have the same number of moles. I would have needed a balloon that was 13 liters in size if this was the pressure and temperature in order to have that many moles. So for our first problem, we found the volume of our reactants. Since we couldn't get them in weight, they came as a gas, so we needed to measure the volume necessary to create this much of our product, 27 grams of ammonium chloride. All right, let's try another one. Same reaction. We're still 1 to 1 to 1. But this time, we're going to make 14 grams of ammonium chloride. And we want to know how much energy was released. This reaction gets hot. It has a negative delta H. The atoms lose that much energy, so it gives it away to the rest of the world. The rest of the world gets hotter. And so if your hand was near it, you would feel the heat coming off of it. We want to know is how much energy was released. So go ahead and pause, solve that energy change. All right, so if you're back, well, first thing first, if I want to compare a chemical to the energy, I need to know how much chemical. And again, masses aren't how we compare one chemical to another thing. We need to be in moles. And so our first step is find moles. 14.0 grams of NH4Cl, and it is 53.49 grams of ammonium chloride in every 1 mole of ammonium chloride. We will find that this is 0.2617 mole, 3 sig figs, of NH4Cl. So over moles of ammonium chloride. How do we relate that to energy? Well, that is where our delta H of reaction comes in. Your delta H reaction says for the given reaction, for 1 mole of ammonia and 1 mole of hydrogen chloride, making 1 mole of ammonium chloride, you should lose 42.1 kcals of energy from the bonds. Well, that is an amount that is given away. That is an amount that goes out to the rest of the universe. It is not contained in the bonds anymore. For all intents and purposes, it's a product. Remember, if your delta H is negative, your atoms gave it away, so it's no longer in them at the end. It's free floating in the rest of the universe. Despite that it's not something we can put in a real balanced reaction because, well, where is it on the other side? You can treat it like it's part of it for calculations. We have a value of energy that we expect for every mole of ammonium chloride. And so if I have 0.2617 moles of NH4Cl, well, there is a ratio of moles of ammonium chloride to energy, in our case, kcals. For every 1 mole of ammonium chloride, so from the balance reaction, there is 42.1 kcals. I have about a quarter of that, so I should get about a quarter of the energy. And what we find is that it is 11.02 kcals of energy. And we'd said 3 sig figs, so it is about 11.0 kcals. When this reaction happens, when we let those liters of starting gas react with each other, it will give off an enormous amount of energy, 11,000 calories. So if we have the delta H of a reaction, we can treat it like it is part of the balanced reactions in order to find the amount of energy. In this problem, we're going to use the heat to solve the starting materials. So we could do a container where I have a box, there's a spigot on top, and I can mix things. And that box, I could surround it in another container that has water. And you could put a thermometer in there and you could measure the temperature of that water. When we do this reaction, it gives away heat. In our last example, we saw it gave away 11 kcals of heat. Well, that heat goes into things. If you've got water around it, it's going to go into the water. It's going to heat up the water. And so we're going to do an experiment where we have a box that is 19 liters in volume. So the volume in here. And there is 2.5 kilograms of water surrounding it. And we're going to assume all the heat of the reaction goes into the water. As long as your little bulb and whatever material is very small in terms of mass, most of the energy is going to go to the water. It's not a bad assumption. Well, in our case, the water starts at 20.0 degrees Celsius and goes up to 23.5 degrees Celsius. Our question, what we're going to solve first, is find the mass of NH4Cl produced. So we're going to put ammonia into our container. So some of that ammonia is going to go in. We're going to have some NH3 floating around. We're going to take HCl. We're going to pump it in. It's going to start reacting. They're going to mix with each other. They're going to do whatever they need to do for a little while. And then in the end, we're going to have some NH4Cl. In the process, it will give heat out to the water. The water will get hotter. Our thermometer let us see that temperature change. So based on all of the heat of reaction going into the water, can you solve how much product I must have made? Go ahead and pause and give that a try. All right, if you're back, if I want to know how much product I made, well, if I knew the energy that the reaction produced, I have a balanced reaction, or at least I can include it in the balanced reaction, that relates energy and product. I need to know how much energy was released by the reaction. If I know the energy, I can say it's 42.1 kcals per mole of product. So the question is, can I find that energy? Well, we assumed all the energy went into the water. So my change in energy of the water must equal the energy of the reaction. So my mass times my S times my T. This is how we find the energy of a temp change. And all that energy came from the reaction. So for my water, there is some amount of energy, Q. It's based on the mass of the water. Well, 2.5 kilograms of water is 2,500 grams of water. The S value for liquid water is 1 small c calorie per gram degree Celsius. And our delta T is our final 23.5 minus the initial 20.0. So 3.5 degrees Celsius. How much energy went into the water to get it to heat up those 3.5 degrees? 2,500 times 1 times 3.5. 8750 small c calories. So this is the energy that went into the water, and we're assuming that all of the energy of the reaction went into the water. Well, if we want this in kcals, remember there's 1,000 calorie in 1 kcal. So divide by 1,000, this is 8.75 kcals. So we know the kilocalories that a reaction must have released. And I have a balanced reaction with a delta H value that tells me it was 42 kcals per mole. So I take my actual energy, 8.75 kcal, and I say it should have been 42.1 kcal in 1 mole of NH4Cl, which nets us 0.2078 mole of NH4Cl. And if we wanted, we can turn that into weight. 1 mole of ammonium chloride was 53.49 grams for 11.11 with 2 sig figs, still following along, so 11 grams of NH4Cl. I'm going to identify how much product we must have made. Well, one thing about that container was that we knew the volume of it. And in theory, I knew the starting temperature of it. If it's surrounded by water, it's probably the same temp as water. So I knew a volume and I knew a temperature. And because I know the products, I can figure out the starting materials. I can find what pressure the gases must have been inside that container. So way at the beginning, when I had ammonia in here, and I had HCl in here. Well, they're not in a balloon that can expand, so they were set for their volume. They must have had a pressure that they were at. So let's take this same info, and let's find what pressure those gases must have been at. Let's just find the collective. That container held both gases, so it had all the pressure of both gases. So our next problem, go ahead and pause. With a 19-liter container at 20 degrees Celsius and with all of our gases in it at the start, what was the pressure of that container? All right, if you're back. Well, I have a container. It's 19 liters, so I know my volume. It was 20 degrees Celsius, so I know my temp. I need a pressure, that's what we want to solve, so I need some moles. Well, I know the product. If I know how much product I made, I can use it to find how much starting materials I must have added. Granted, you possibly could have added more and had a limiting reagent problem, but we weren't asked to do that here. We're assuming we added just enough of both components. Well, as we saw in our original calculation, because it's 1-to-1, that is 0.2078 mole of the ammonia and 0.2078 mole of the HCl. Because all the products and reactants are 1-to-1, it was the same number of moles. Well, both of these are in our container, so it's really the sum of both of them is the total number of moles in the reaction. The total number of moles that were in our container at the beginning. So it's the sum of both. 0.4156. So 0.4156, and we had 2 sig figs at that point. I want pressure on its own. PV equals nRT. I need to move the volume, so I divide it over. My moles, 0.4156. My R value, well, it depends what pressure we want. Maybe you chose a different one, but let's do atmospheres since we've been doing that this practice. 0.0821 atmospheres, liters, mole Kelvin. My temperature, well, can't use 20 Celsius. 20 plus 273 for 293 Kelvin. 293 Kelvin. And my volume was 19 liters. So my moles times 0.0821 times 293 divided by 19. What we find is that our pressure is equal to 0.526 atmospheres, or about 0.53 atmospheres. So the pressure in the container was not all that significant. It's easy enough to get something up to half an atmosphere. But we can use just that energy to heat water that we started with to calculate all these different components. By knowing how much the water got hotter, we were able to find the total energy that went into water. Well, that energy came from the reaction, and we know how much energy 1 mole of product should have made, so it let us know how many moles of product we actually made. All of that product had to come from starting material, so we can find the amount of starting material. And if we know the amount of starting material and they were the gases, we can solve what their pressure in that reactor must have been. So here's a few different aspects of combining stoichiometry, gas laws, and energy.